I was little disappointed with the disruption. Okay. Now, what is a sequential circuit is quickly. We have already studied what is a combinational circuit is, right? What is a combinational circuit? It will have a lot of gates. In addition to the gates that you have, which is nothing but a combinational circuit, you will also have a memory element. So that is the only difference in your sequential and your combinational circuit, which means that these kind of sequential circuits can remember some data. So there are certain characteristics of a sequential circuit. What are the characteristics? These are the three characteristics. That is, the memory element that you have must be able to hold a value. Hold means like it must store a value. You must be able to look at that particular value, which means reading the value, and you must be able to change the value also. Now, the immediate question that will come is, how can a circuit with just gates can do all these things? How can it hold a value? How you can read a value? Obviously, reading is possible, and how you changing is also possible. So first, when we attempted to design a circuit that can hold a value, what is the logic? I'm having a combinational circuit, say for example, a NOT gate here. I want a circuit, if I'm giving 1, I'll be getting 0. So how do I make this hold this particular 1 value in the circuit? So the logic behind is create a loop. How do you create a loop? So a NOT gate is created one more, and then you create. So you take an output from here, right? So this particular circuit will always have this 1 value. So we are holding a value. If you take a tapping and then read out what is the output here, then you can read the value, right? So that was the logic that we followed in the last class. So we created a circuit which can loop together, and this is an equivalent circuit model. This circuit can perform 2 out of the 3 properties that we listed. What are the 2 properties? It can hold a value and you can read the value. So we took an example of a single bit circuit, and then we designed this simple circuit. What about the third characteristics, which means how do you change the value? In order to change the value, we should not use a NOT gate, because NOT gate has got only 1 input and 1 output. If we can have a gate which has got 2 inputs and 1 output, then you can definitely change the value, which means that we replaced this NOT gates using NOR gate like this. Please note here, reset is at the top and set is at the bottom. So with the help of this reset and set, you can change the value. You can give 1 here, you can give 0 here, or you can give 0 here, 1 here, you can give 0 here. Any 4 possible combination you can give. Thereby you can control the output that you get across the gates. So 3 properties we have successfully done. This circuit can hold the value because of this feedback loop here. You can read the value through this Q and Q bar. You can change the value through this R and S. One thing that you must note here is, please recall, where is your R and where is your S? There is a meaning to it. R is at the bottom and S is at the top. Normally, these kind of flip-flops, they are not called as RS flip-flop, but they are called as SR flip-flop. Obviously, set and reset rhymes better instead of reset and set, right? So set and reset flip SR, we normally call such kind of flip-flops as SR flip-flop. But the initial design that we have done using an OR gate was an RS flip-flop. Obviously, we will be changing this configuration to an SR flip-flop because there are certain disadvantages with this particular configuration. What are those configurations? If you analyze this particular circuit for different values of R and S, we came to a conclusion in the last class. Obviously, we got the Boolean expression and then we came to a conclusion. Let me go to the conclusion now, because you can always read or you can look at the previous class notes. So these are the 3 input combinations that we made for R and S. So when your inputs were 0 and 0, your output should not change. This is okay. When your inputs are S and 1, which means that when your reset is 1, your Q value is reset. When your set value is 1, your Q value is set to 1. Now the last condition, which is 1 1 condition, we created a characteristic table also. Please understand the difference between characteristics table and a state table. So this is the characteristic table which will summarize and give you the nature of the behavior of the flip-flop. The state table, this is called as a state table. This table will give you the all possible combinations of input and outputs. Okay. Now we analyze SR equal to 1 1. Now there were two problems associated with this. What is that? When you give 1 1 as an input to RS flip-flop, then your output were going to be 0 and 0, which is contradicting the basic principle of the complement. Q should be a complement of Q bar and Q bar should be a complement of Q. But when you give 1 and 1 as an input, it was your outputs were 0 and 0 here. Your outputs were 0 and 0 here. And when again this 0 and 0 were fed back as a previous state input, then your output was becoming 1 and 1 here, which means that when you are giving 0 and 0, when you are giving 1 and 1, your outputs were 0 and 0. When you are giving 0 and 0, your outputs were 1 and 1, which means that this was going into an indefinite loop. So this 0 is fed back again here and this 1 is again fed back here. So this was going on indefinite into an infinite loop. So we should always avoid the last case, which is SR equal to 1 1. Obviously, this is a serious disadvantage, right? You cannot ask the customer to avoid a particular input, otherwise your circuit will become malfunction, then you will require a servicing. If somebody says that when you are purchasing a laptop, please don't press the spacebar button, otherwise you will have to service every time. This cannot happen, right? So how do you avoid this particular problem? What people thought is, then people thought that it must be because of this NOR gate usage, we came into this problem. Why not? There is another universal gate, which is called as a NAND gate, right? Why not we use a NAND gate? Okay. Then people started to design a NAND gate. When you are using a NAND gate, the input combinations, the gate logic of a NAND and NOR, they are different. Am I right? So quickly, let us draw the truth table for a NAND and NOR. I'm going to do it for a NOR. So A, B, and Q is the output, right? So let us, instead of A, B, let us make it as S and R. Okay. I think AB will be better. Okay. So NOR output 0, 0, 0, 1, 1, 0, and 1, 1. So 0 plus 0, 1. 0 plus 1 is 0, 0, 0. This is the NOR gate output. Now the NAND gate output, this is, yeah, Q NAND, right? This is NOR. So 0 and 0, 1, 0 and 1, 1, 1, 0. Okay, so this is how the gate is, which means that your input, instead of S and R, we have to change it to S bar and R bar. If we change it to S bar and R bar, then what happens is, except these two inputs, your actual inputs become changed, right? So we replace it with S bar and R bar because we are using a NAND instead of NOR. When we use A bar and B bar here, then everything gets reversed, right? So then the problem will happen only with this 0, 1 and 1, 0 inputs. Otherwise, both these inputs are same. So now when you change your input, please note this was initially R and this was initially S, because RS flip-flop. That is why I asked you to remember that it was R here and S here. Now, because we have changed, we have interchanged our R to S bar and S to R bar, right? So if you want to understand much better, what you do is you create an RS flip-flop and then Q as an output. Okay, now you modify this inputs to S bar. Okay, maybe we will write. So R and S input, right? So when it is 0, 0, no change. When it is 1, 0, your Q was 0. When it is 0, 1, your Q was 1. And 1, 1, let's not write. Now, what is that we are doing? We are replacing this R with S bar, and we are replacing this S with R bar, and at the same time we have replaced our gates also, right? So this is using NAND gate. Now let us see what will happen when this is 0 and 0, right? What is the output of a NAND gate? So when this is going to be 0 and this is going to be 0, your NAND gate output will be 1 here, right? So it's 1, and this will also be 1, 1 and 0 for 1, 1. Okay, so we have to match your S bar R bar flip flop to RS flip flop. So when you do this particular arrangement, your input becomes S bar and R bar. So 1, 1, it is equivalent to 0, 0 in RS flip flop. So there is no change. When it is 1, 0, please remember S bar was initially R and R bar was initially S. So it is a reset button. So Q is reset. So now your set is 1 here, which means R bar is 1 here. So it is set. 0, 0 should be avoided. This is the state where RS was equal to 1 and 1. But again, this is really confusing to look at S bar as 1 as a reset. Similarly, R bar as 1 as a set. This is confusing. If it is S and R, then it would have been easy for us, right? So what we do here is we created a gated SR latch, which means that we are going to invert this S and R, is S bar and R bar. If you want to invert this S bar and R bar, what you can do is you can put an inverter here. You can put an inverter here. And obviously inverter, how can you model an inverter using a NAND gate? You can model an inverter using a NAND gate like this. So this is also an inverter. So you can replace this. But again, people thought, why do we waste the another input of our NAND gate? We can have a better control if we use this input also. So what people created was a gated SR latch, which means that the inverter that we wanted, because we wanted to invert this S bar to yes, was used to have a better control now. Now, this is called as a gated SR flip-flop. Now, please see, we have started calling this kind of flip-flop as SR flip-flop instead of RS flip-flop as before. So now it is an SR flip-flop with a better control using a control input. So how does this control input operate? Let us see. When your control input is 0, okay, whatever may be your input, your S bar, this will be 1, this will be 1, which means that this is going to be, we are not bothered about the output Q and Q bar here, no change state. Now, only when this is going to be 1, then this output across S bar and R bar will depend on the S and R values. Okay, let us see how. I'm sorry. Okay, right. Now, when your control input is 1, right? Now your S bar and R bar will entirely depend on this S and R input. And control input is, so this condition 0 is also called as a quotient condition. Okay. When your control input is 1 and S and R are 0 and 0, what will happen? Your S bar and R bar will be 1 and 1. What is the truth table for S bar, R bar, 1 and 1? There is no change. So there is no change here. Now, when control input is 1, 0 and 1, your S bar and R bar will be complement of S and bar. It is 1 and 0. So S bar 1 corresponds to 0 reset, right? As in this particular table, S bar equal to 1 corresponds to 0 reset and 1 for R bar corresponds to 1 here. So 1 corresponds to R bar here. So S and R, 1 and 0 corresponds to set. Now you relate S input with Q, because we are not bothered about S bar and R bar because we have complemented it. So when it is 0, 0, there is no change. Very nice to see. When it is 1 here, which means reset is 1, your output is also reset. Good to hear. When set is 1, your Q is also set, right? Looks nice. And when both are 1 and 1, obviously this state should be avoided. Okay, so we should not use this particular state. So now this looks nice, right? So from where we have evolved from RS input through an OR gate, we evolved to S bar R bar flip flop, and then we evolved to SR flip flop, right? And this SR flip flop is giving the same kind of response which NOR gate was giving, and at the same time this had a better control because of the control input. This was not having the control input. So now any doubt till this? Okay. I hope I have summarized it much better when compared to the last class. Okay, at least personally satisfied. The flow was good this time. Okay, now let's move on to another configuration. Okay, we are going to use this configuration of a gated SR flip flop now. Now we are going to modify this. Modify in the sense we don't want this thing to happen at all, right? 1, 1, 2 happen. So people started modifying these kind of circuits. As a result, what is the objective of having this flip-flop? We must store the data, read the data, and change the data. So then why do you have two inputs, right? So then what people did is they just clubbed this together. They clubbed this together. When they clubbed this together, which means, let us see what will happen. So to eliminate, then the people created a latch called as a D latch. D represents data. D represents data latch. To eliminate the undesirable condition in the indeterminate state of SR latch, please see here it is SR1. To ensure that inputs are S and R not at the same time, and this D latch is also based on an S bar R bar latch. It will have only one input. So what is the change in the configuration? Simple. You club this. This is based on an S bar R bar latch as listed in the points. This is your D flip flop now. We have modified our SR flip flop to a D flip flop. What did we do? We just shorted these two inputs, and our input is no longer called as SR. Our input is called as D. This is based on again the S bar R bar latch, and instead of having two inputs, it is having only one input now. That's what has been listed here. It is based on an S bar R bar latch, and it will have only one input. Now, additional gates, they will generate the different signals here. But let us understand now, still the control input is still there. Now let us see what will happen. When your control input is 0, okay, and D input is 0, what will happen? Your S bar and R bar will be 1. When it is 1 and when S bar and R bar are 1, then Q and Q bar, there will be no change, right? It corresponds to the first state. When control input is 0 and when S bar has been combined to 0, which means that both are 0 now, your S bar and R bar will be 1, there will be no change in your output. Now, when you give, okay. Now, when your C is 1, now we are changing our control input to 1. Okay, there is a slight change. This corresponds to T flip-flop. Instead of the shorting, we will complement the other bit. Why did we do this was because we want to avoid the last state, right? 1 and 1. So when S is 1, if we make the other one to complement, we will be using only these two inputs. So that is the reason we have complemented this one. We have complemented this so that we will avoid the first state and the last state. Okay, so this forms D flip-flop. Sorry about shorting that. So this forms the D flip-flop now. Now let us analyze. Now when your control input is 1, what will be your latch output? Your latch output will correspond either to 1 or 0, right? Now let us look at the truth table now. My control input here okay. Now my control input is 1. Obviously, we have removed this particular state and this particular state by complementing one input with the other. When my control input is 1 and when my S input is, sorry, this has been combined to D now. When D is 0, what happens? D is 0, your R will be 1 here, S will be 0 here. So you are resetting it. When D is 0, you are resetting it. When D is 1, then you are setting it, right? So now combining the states here, when your control input is 0, when your control input is 0, okay, when your control input is 0, we are not at all bothered what is our this D value is, because when this is 0, obviously there will be no change across your Q output. When your control input is 1 and D is 0, your Q output is 0, which means you are resetting it. When your D is 1, you are setting it. Now if you compare this D to Q alone, what happens? Whenever your control input is 1, whatever you are giving it as 0, you are getting the same thing across your output also. So just it follows a data transfer from D to Q with the additional properties of what are the properties which can hold the data, which can you can read the data you are reading through Q, you can change the data, you can change the value of Q. In addition to that, you can control also, right? So we have satisfied all the properties of memory here. So this, the other name of this kind of latch, they are called as transparent latch, because Q follows D. There are two main advantages with this particular D latch. What are the two advantages? There is no more meshing with same kind of inputs, right? So one input is set and other input is always reset. The other thing is no bad combinations are possible here, because at any point of time 0 and 0 and 1 and 1 are completely avoided. Okay, so these are the two advantages with this particular D latch. Every time I'm not saying flip-flop, I'm saying latch. Now what is a flip-flop? The disadvantage with the latch is they have a huge synchronization problem. What is it? What do you mean by a synchronization problem? Let me quickly recall what is the function of a latch in different perspective. What is the function of a latch? Why we are calling this as a latch is an immediate circuit, which means that it is very responsive circuit. Responsive in the sense you give 1 here, it will give 0 immediately, which means these gates are not going to wait for anybody else or any other inputs to perform. This is nothing but a simple combinational circuit, right? So, which means as an engineer, you must be able to control the flow of this particular data. Whereas in case of a latch here, you are not controlling it. Whenever you are giving input, what will happen? Immediately this NOT gate will calculate. And if you have a control input also here, immediately this output will be there. And once you have this Q output, this will also, you will have an output here. You are not controlling any of these particular gates. Obviously, we are controlling through an external input, but this control is not what I mean. We would like to have the flow of the data from one stage to the other stage at a regular interval of time. Okay, so the first let us go to the disadvantages of a latch. Latches, though they are transparent in the sense any change that you do as an input, immediately you will get across your output. This will create the synchronization problem. Yes, obviously, why the synchronization problem will be there? Because am I audible? There was a power failure. Can you see my screen? Okay, if you are unable to see the screen, just ping me up. Okay. So, okay. So what is that we are trying to do? Am I not audible? $228. So just a second, my laptop. It got. I don't know what happens. Okay, thank you, Kritika. It was a power failure, but my softwares are also. But it was a good summary that I gave. At least personally, I'm satisfied. So just hold on, let me open the file again. All right, great. So these kind of circuits, we call it as a transparent latch or D-latch. So the main advantages of these were we no need to mesh with two same inputs and we are avoiding the bad outputs. Then the disadvantage with the latches is they create a synchronization problem. And how do we avoid the synchronization problem is the same latches can be used to create a flip-flop that can respond only at a specified time instead of any other time. Say for example, what do you mean by that is, I'm giving an input of 1 here. You might give one put, but this will the complete circuit will respond only at a specified interval of time. Let us assume that we are having a switch here. Okay, we are having a switch here. You are giving one here, but only if some, say for example, there is a controller. You can take exam anytime, but only when controller of exam releases his timetable, you can take the exam. So there is a control here. So here also, you might give one here, but the closing of the switch, if somebody else is having the control, only then this particular circuit will operate. So if say for example, I have the control, you are performing a lab and you have given the input and you are calling me. Only if I give you the key, you can close this particular switch, let us assume, right? Then your circuit will operate. The same logic is used here also. But every time you cannot have a manual switch, right? So what can be an automatic switch? An automatic switch is something similar to something we call it as a clock. How does this particular clock will respond is, say this is nothing but a digital clock, which means that this will create an output of 1 at specified interval of time. It will create some pulse signals just like this, which means only when your clock is 1, this is 1 value, this is 0 value. 1 means analog value is 5 volts and 0 volts. This is 1 value, 0 value, 1 value, 0 value, 1 value, 0 value. If you know, in analog electronics, there is a circuit called as oscillator. These oscillators are the circuits that are used as clocks in digital circuits. The function of this oscillator is to generate the square wave pulses. You know, sinusoidal pulses, right? So this the oscillator circuit will create, but you can also create square wave circuits like this. So these are nothing but used as a clock signals here. So instead of this manual switch here, if you feed all these inputs by, say I'm having a clock signal which generates the square pulses like this. If I control all the gates using this clock signal, which means that all the gates will work only when you have a clock pulse high. So your one input. So what will happen when during the first clock cycle, every gate is allowed to operate. So this one will get transferred to this state. Then during the next clock cycle, second clock cycle here, this gates will operate. So this one is transferred to the next gate. Now you have a better input. So so now we are avoiding the synchronization problem, right? So what is a flip-flop is? A flip-flop is a circuit that can maintain a binary state indefinitely, okay, until directed by an input signal to switch states. Okay, now these flip-flop will have two output states. Obviously, your latch is also have two output state. Now the difference between your latch and a flip-flop lies here. So what are the properties of a flip-flop is? It will have a two outputs states, which is one is complement of the other, Q and Q bar. You may immediately ask me, sir, latch also has the same kind? Yes, but the last difference lies here. I'll come back to this. So since they are having two kinds of outputs here, they are called as bistable devices. One is complement of the other, so they are called as bistable devices. Now your flip-flops, because we are giving a feedback to our input side, right? So your current input will depend on the previous input. So instead of input, current, previous, we are going to define states now. Q of t corresponds to present state, that is at this particular instant of time. And after the next clock cycle, we are going to call it as a Q of t plus 1, which corresponds to next state. In addition to this, latches has got a memory element with a clock signal, nothing but your flip-flops, and these flip-flops are the one which are called as memory, actual memory. What happened? Okay. Okay. These flip-flops are called as memory. So to summarize, you are having a memory element, which is nothing but your flip-flop here. You are giving a command, say for example, the inputs are called as commands. Presume that this is a D flip-flop input, and you are getting a stored value as an output, which is controlled by a clock. Now for next few minutes, let us focus on this particular clock. Now, I've already said you how these particular clocks will work. Clocks are usually square waves. So you must understand how the square wave will look like and certain terminologies of a square wave. Your square wave will look like this one. There are three things that you must know. The flat surface here, the flat side, flat value. These are called as positive pulses. You don't have anything like a negative pulse in digital electronics. Negative pulse means what? Because if this 0 volts is your reference, this is how your square wave is generated. which represents plus 5 volts and minus 5 volts. But we will consider this to be our reference actually. So which means that you will have 10 volts and 5 volts, 0 volts as a reference. So we don't use the negative pulses in digital electronics at least. So the levels ones, they are called as positive pulses. And the other thing that is of very important to you is the one, these kind of edges. This edge is rising from 0 to 1. There is another edge here which is falling from 1 to 0. Again, the 0 is rising to 1, 1 is falling to 0, rising to 1, falling to 0, rising to 1, likewise. So these rising edges are called as positive edges. These falling edges are called as negative edges. Why I am emphasizing on this is because there are certain circuits which will get triggered when you have a positive pulse, which will get triggered when you have a negative pulse. We will see that now. Next, what we see here is the activating your flip-flop or triggering your flip-flop. The latches or your flip-flop, obviously you know that it can be controlled using a control input, but that control input is only for the first stage of your flip-flop. What do I mean by first stage of your flip-flop? This particular stage only, not the next stage. And at the same time, it doesn't control your input actually. It controls the gates. So, okay. So now these flip-flops, all the gates now will be activated by using a trigger pulse. This trigger pulse, or what is a trigger meaning, is the momentary change that you have in your clock is a trigger pulse, which means that we are going to look at the transition to trigger the pulse. These pulses that I said you, the rising edge, these transitions that you see here, either it is a positive transition or a negative transition, we are going to use these transitions for triggering our pulses. So to to summarize, there are classifications of these kind of pulses. Either this triggering can be a pulse triggered. The other name of a pulse triggered is a level triggered. What I mean by that is, in the square waves you have, that is your flip-flop can be triggered when it is having a flat value during these values, or you can trigger it when you are having an edge triggered, right? When there is a transition taking place. So to classify the types of trigger, either it can be a pulse triggered or a level triggered, or it can be edge triggered. Don't jump to the edge trigger now. I am going to define some important things. So this pulse triggered can also be either a positive level triggered or negative level triggered, which means you can trigger your flip-flop when you are having a positive side, or you can trigger your flip-flop when you are having a negative side. Okay, based on that, they are classified as positive level triggered and negative level triggered. And the most important is your latches uses the pulse triggered scheme, which means that when on, it means that the clock is 1. When it is off, your clock is 0. This is on position, this is off position. Now coming to edge triggered. Edge triggered are normally used in flip-flops. Right? There was one question in your mid-semester exam also, whether it is edge triggered or level triggered. There might be errors in certain things. Always you should refer to multiple texts. Okay. Now, when coming to edge triggered, they are again classified as positive edge triggered and negative edge triggered. What do you mean by positive edge triggered is when your pulse goes from 0 to 1, it is called as positive edge triggered, and this corresponds to on value. You are onning your flip-flop. What is a negative edge triggered is when your transition takes place from 1 to 0. We call it as an on and off other times. Off other times means what? If it is going from 0 to 1 also, when you are using a negative edge triggered, it is considered as off. So to represent in a clock signal, this is how the positive edge triggers are, right? So whenever you are having a positive transition, your flip-flop will activate. In negative edge triggered, whenever you are having a negative transition from 1 to 0, then your flip-flop is activated in negative triggered flip-flops. So what are the four kinds of flip-flops we have? I mean, we have not studied one of the kind, but there are four kinds of flip-flops. SR flip-flop. We have just studied SR latch only. We have not studied JK latch, but we will study an important flip-flop here. A D flip-flop and a T flip-flop. We created this SR flip-flop from SR latch. We created this D flip-flop from SR flip-flop. Once we have D flip-flop, we can have JK flip-flop and T flip-flop. So to see how they look like, I'm just representing them in blocks. I'm just going to tell you first, how does the positive edge triggered flip-flop will look like? So this is an SR flip-flop. I have an S input, R input, Q input and Q bar output. This is JK flip-flop, right? The internal configurations are different. Don't worry about that. We will anyway dealing with these JK flip-flops. And then you have a D flip-flop. D flip-flop and SR flip-flop are similar. Only thing is the inputs are, you can convert this SR into a D flip-flop. How? Just short it down through a NOT gate. This SR flip-flop will become a D flip-flop, right? And T flip-flop is a part of a JK flip-flop. Please remember JK's configuration is slightly different from SR's configuration, and T flip-flop is derived from JK flip-flop, whereas a D flip-flop is derived from SR flip-flop. And all these, you can see one peculiar thing, that I'm having some symbol here, right? Some symbol here. What does this mean? It means that this is a clock signal. When I write a symbol like this and write a C here, somebody will write C, somebody will write CL, somebody will write CLK, right? It is a clock signal. And these are called as positive edge triggered clock. And what is a negative edge triggered clock? Only difference you have in a negative edge triggered clock is you will have a bubble here. You will have a bubble here, and this represents that this is negative edge triggered clock. Now you must be familiar with how this circuit symbol will look like. Okay, now we have studied SR flip-flop. Just we will move on SR latch. We will just move on to SR flip-flop now. What will be the difference from SR latch and a flip-flop? You will have additionally a clock signal in an SR latch to get an SR flip-flop, and they will be edge triggered. So what are the inputs you are going to have, and how the triggering is going to take place is SR represents S for set and R for reset. When S is high, your output your output Q will be equal to 1. When R is high, your output Q will be equal to 0. Okay, which means that when S is high, when S is 1, your R will be 0, and which we call it as a set state. When R is 1, your S will be 0. We call it as a reset state, and your Q will be 0. And these are some peculiar inputs. When S is 0 and R equal to 0, there is no change in your input. When S is 1 and R is 1, it is an invalid input. We should avoid this. Now let us look at the truth table, right? I have not given you the circuit here. Right? Yeah, this is how the circuit will look like. The only difference is, instead of a control signal here, we are having a clock signal. So your gates here will operate only during the edge pulses of this particular clock, which means that I'm just slightly zooming in. Okay. I should not have done that. Okay, I will not do anymore. Right. It went somewhere. Yeah. So I'll just So this is your clock that will control, and this is edge triggered, positive edge triggered, in the sense only during this transition from 0 to 1, this gates will operate, and that is why this is called as a clocked RS flip-flop. And this particular section, there is a master and slave flip-flop also, where the same clock pulses are given to these gates also. In that particular case, this will be called as a master flip-flop, and this will be called as a slave flip-flop. Don't get confused. We will revisit this particular part later. So I'll immediately erase. Okay. Now let us go back and look at the state table or a truth table now. Before that, the characteristic table of a positive edge triggered SR flip-flop. Now, instead of a control signal, we are having a clock signal here. When there is no clock and when your inputs are 0 and 0, there will be no change across your output. Q of t plus 1 represents the next state, and we are going to represent our next state in terms of the present state here. That is what is called as a characteristic table. Next state will be represented in terms of present state. And when your clock is 1, 0 and 1, please see your reset is 1. So your Q of next state must be 0. When your set is 1, then it is 1 here. When both are 1, it is an invalid state. Now, what will be the characteristic equation? From this table, how do you write the characteristic equation? If you want to write the characteristic equation, you must know the complete truth table or state table of this characteristic equation. What do you mean by complete state table? We have to consider all possible values of your present state also. That is what is meant by the state table is. So now let us create the state table now. So I'm having a clock and I'm having a Q of t, which is a present state. S and R are our inputs and Q of t plus 1 is our output. Please, for the sake of convenience, let us put all our clock signals to be 1 here. Why? Because we want our flip-flop to be active. We already know what will happen when it is not active, right? Where there will be no change here. So we are going to concentrate only on the active clock signals. So when your SR input is 0 and 0 and your Q bar input is 0, then there will be no change in your output, right? So what will be the no change means your Q of t is 0. So your Q of t plus 1 is also 0. Now let us look at the other possible case. When it is 0 and 0, concentrate here. And when your Q of t, that is the present value, is 1, again there should not be any change. It should be 1. Please compare these two states, this and this state. Now similarly, when your present state is 0 and when it is 0 and 1, which means that we are resetting, while we are resetting, we are not at all bothered about what is our present state is, just it is 0. Hence, this is also 0. Similarly, in this particular state 0 and 0, though this is 1, still it is 0. Similarly, when this is 1 and 0, we are setting it. Similarly, when you are 1 and 0, we are setting it and we are not at all bothered about our current input here. Now let us look at the last state when it is 1 and 1. Whatever may be your present state, it is an indeterminate state. We should avoid this. Okay. So this gives us a complete truth table. This gives us a complete truth table. So once we have a complete truth table, it is easy for us to create the K-map. So when you create a K-map here, so this corresponds to 001x, right? 001x, 001x, 101x. So 101x. Somebody has got a doubt? It is still blinking. Okay. God knows. Okay. So now we can create a Boolean equation from this K-map here. So how you can combine? You can combine these 4 ones and then this 1 is alone here, so we can combine with these two columns. So when you write the q of, so this expression, this came up is for q of t plus 1, right? This is for q of t plus 1. So q of t plus 1 can be written as one value is q of t, because the row wise is q of t. So q of t plus 1 can be written as this quad corresponds to s, and this two cells combination corresponds to q r bar. Okay, so this Boolean expression gives you this truth table now. So this equation is called as the characteristic equation of flip-flop. Why characteristic equation? Because we have derived from the state table, and the state table in turn is derived from the characteristic table. Okay, so I have defined few terms now. Should we touch D flip-flop? Okay, 3 more minutes, we will touch D flip-flop. So now what is the, we have just studied RS flip-flop. So next is a D flip-flop. It will have only one single input and the D corresponds to data. What is the only difference? We can have a NOT gate here, shorting this S and R through D, and instead of the control input, you have a clock input. That is the only difference. Now, if you draw the characteristic table, if your input is 0, obviously we are going to consider our clock to be 1 and 1. If your clock is 0, then whatever may be your D is, it is no change case. So we are not bothered about when clock is 0, right? When your clock is 1, when your input is 0, your Q next state Q value is 0 because it follows your D value. When your D is 1, your next state value will be 1. So this is a characteristic table. We must create a truth table. Truth table in the sense we must add the present state value of Q also. So the characteristic table now, the state table, sorry, this is a state table. The state table now will have, so when your Q can be, your previous state can be 0, and if your present state is 0, your output is 0. Your previous state may be 0, and if your D value is 1, your Q of T will always follow your D value. It will always follow your D value. Whatever may be your previous state, it is not, we are not bothered about the previous state at all in case of a D flip-flop. So the Boolean expression now, writing the Boolean expression for this, this looks like an XOR flip-flop, right? Something similar. Yeah. So these are the two ones here. This corresponds to Q bar D, and this corresponds to QD. So you can take D as a common, which is Q plus Q bar. So Q plus Q bar is 1, so it is D. So Q of T plus 1 corresponds to D. So D flip-flop just transfers the data, and this next state of your next state output is not at all dependent on your present state of key. It is not at all dependent, right? So this is what is your D flip-flop is. So next we have JK flip-flop. We will continue in the next class. Any doubts? Okay, so there are no doubts. We will see in the next class on Monday.